example, W net equals delta K. Applying this means that you will see that there are three forces in the direction of the motion. There's an applied force up the incline, there is a frictional force against the movement down the incline, and there certainly is a weight, because there's a weight acting at an angle at an incline. The normal force don't have an influence on the work done because it is perpendicular to the motion. It is cos 90, so it is 0. So this normal force, although you can include it in your application of W net K, according to me, in the final exam, I don't bother. I advise learners don't include that in your calculation. There's no mark on that, and there's no penalization for not showing it because that force is acting perpendicular to the motion. So, three forces: the work done by the frictional force, the work done by the applied force, and then the work done by the gravitational force. Now, depending on which information you will have, you will see which formula you are going to use the work done by the gravitational force. If I elaborate on the work done by the frictional force times the distance moving up this incline, and then cos theta. Now cos theta, when there's friction, a frictional force acting, work done by frictional force, this will always be cos 180. If this is applied force and the object is moving in the direction of the applied force, that will be cos 0. And now, if you have the motion up the incline, and you want to calculate the work done by the gravitational force, you must get the component of the weight in the direction of the incline. So therefore, it will be Fg cos theta, and you will realize that that gives you the horizontal component of the weight, and times the displacement. It can be delta x actually here, but you're not penalized. We don't penalize for delta x or delta y, vice versa, but I will advise to write down delta y. So then you have the component of the weight, and you can calculate the work done by the gravitational force equals delta K. If you apply, and we're nearly finishing this topic, if you apply or ask to apply, or that is your choice, and remember, nowadays they very rarely force you to use one specific formula, or the work energy theorem formula maybe, or the formula for the work done by non-conservative forces. Normally you have the option which one you want to use, and you must maybe working through examples, if you have a choice, get to a formula that maybe works easier for you. Many a times, if it's possible, I prefer to use this formula, WNC, the work done by non-conservative force, is equal to the change in kinetic energy plus the change in potential energy. Preferably, if you have height available, so you can calculate the change in the height to get delta EP, I will prefer maybe this formula. Now you will see in this application, you don't have, like in the work energy theorem, one of the components of work done is the work done by the gravitational force. Now that part is being moved to this delta EP. So the work done by the gravitational force now is being calculated by the change in the potential energy. So now your only two non-conservative forces is a frictional force and the applied force. That is the only two non-conservative forces, because gravitational force is a conservative force. So that is been dealt with this change in height or potential energy. So this is the two possibilities, the two possible formulas that you can apply. You can apply both. You must decide which formula are going to work easier in a specific example. Now, the last part, maybe on work energy now, is the conservation of mechanical energy. And the conservation of mechanical energy only applies in the absence of a non-conservative force. That means if you apply the conservation of mechanical energy to this formula WNC equals delta K plus delta EP, then it means that this part, this WNC, immediately becomes 0, and then you can apply this formula to conservation of mechanical energy. If you rewrite all these terms, you basically get to this formula that at the end I prefer you must use when calculating a situation where there is conservation of mechanical energy due to the absence of a non-conservative force. So what does that state? The potential energy initially plus the kinetic energy initially equals the sum then of the potential energy plus the kinetic energy at the final point. So at point A or point B or initially, finally, you can use different symbols here. It can be A, and then it can be a point B. You must just look at the example, but just indicate that that is at a certain point A, or initially, or a certain point B, or finally. You must at least have a symbol that distinguishes between initially and finally, or point A or point B. And then you just substitute the values into that formula, and there will be one unknown, and you can calculate either the final velocity or the final height, etc. So it's very important. No friction or applied force can be present in the example if you want to apply this formula for the conservation of mechanical energy. Now, tension force can be present when using that formula. I'll maybe at a later stage refer back to that one. Now, what is common errors? And I think that will conclude the part on work energy. Very, very simple errors. And sometimes if your teachers were able to see what you have done, you must remember you are working with change. The change in the kinetic energy and the change in the potential energy. So therefore, when calculating, for example, delta K, you can't just substitute delta K with half mv initially squared. You must state it as a change in. So if the final kinetic energy is 0, that it is 0 minus the initial kinetic energy. You can't ignore the zeros when working with a work energy problem and the change in kinetic or potential energy. Secondly, please, this is the correct way if you want to maybe to make your calculation more easier or rewrite the formula for the change in kinetic energy. This is the correct way. Half m in brackets v final squared minus v initial squared. The following is wrong. And sometimes learners write down half m and then they first subtract final and initial and then they square it. So that is certainly a total different calculation. So don't do that mistake. And I think this is maybe the last statement on work energy, please remember, you can't state, there isn't a formula which state the work done by gravitational force equals mgh. You're working with a change again in potential energy. So rather use then the formula to calculate the work done by gravitational force by making use of your basic formula for work done F delta x cos theta, or stating that the work done by the gravitational force is always negative, the change in potential energy. So this is a very sloppy formula for calculating the work done or the change in by gravitational force or the change in kinetic energy. Let me just, okay, I'm concluding, sorry, there's just one slide, if I will conclude with this slide, and that was a question in the November 2017 paper. And what they have done, they have given a question about work energy in a two-body system working across the pulley. So you apply the work energy theorem like normal, but what is the big difference here? You work with the two forces, and now you use a systems approach. When working with calculating work energy on a two-body system, you are allowed to ignore the tension. So that means to apply the system approach to this problem, because the tension force don't play any role in the work done on the system. So you can ignore that, you can apply the systems approach, and you work with the frictional force on A and the gravitational force on B. But then the very important aspect to remember now, the change in the kinetic energy, that W net equals delta K, you must calculate the change in kinetic energy of A plus the change in the kinetic energy of B. So you must take into account the energy changes for both blocks. And that is what I'm going to conclude with. Next time we will move on to the Doppler effect. So that is a comments on work energy, and work energy, which is normally question 5. Yes, there's a question that have their challenges, but please stick to your method of first drawing your free body diagrams and then apply that free body diagram, that forces, to your two basic formulas, W net equals delta EK and WNC equals delta EP plus delta EK. Right, this is my comment so far up to work energy, and we'll have a discussion on the other topics on the next occasion later in November. Thank you very much.